We'll continue our discussion on material dispersion that we started last time. And specifically in silica, because optical fibers are made out of silica glass. So we saw last time, for example, the refractive index varies with wavelength like that, right? So in general, the refractive index for any material, right, as a function of wavelength, can be modeled by what is known as the Selmayr equation. So which looks something like this. Okay. So you take any material and you can actually model the refractive index versus wavelength using this type of equation, where A1, B1, A2, B2, A3, B3 are constants depending on the material. Okay. So this is known as the Selmayr equation. Okay. So lambda typically is taken in micron, the wavelength. Okay, so for example, if you take pure silica, right? So these values look something like, okay, so you can see that they're taken to be extremely precise. Right? So many significant digits here, because again, as we saw, right, over a large wavelength range, so like from 0.8 to like 1.6, this only varied from like 1.44 something to 1.456 something, right? So the change is very small. So basically these constants have to be very, very precise. Okay, so for A2, okay, similarly B, okay. So like almost every material under the sun has been modeled, and these constants have been found out for pretty much any material you can think of. Like, so for example, if you go to this website known as refractive index.info, okay, you can just select any material you want, right? It will give you this curve of the refractive index of the wavelength. It will give you the Selmayr equations and all the coefficients, okay, and you can also get the dispersion, etc. Okay, so do check this out. Basically, you can see that. Yeah, you can do this for any material. And so what one can do is, as I said last time, that so typically we can dope the silica, right? This is for pure silica. So we can dope the silica with some dopants to change the refractive index slightly. Okay, so for example, if we dope it with about 6% germanium dioxide, right? So this is by mole fraction. Okay, so you know that germanium is the same group as silicon, right? Just one row down. So one can dope the silica glass with germanium dioxide quite easily, right? And so, for example, if you dope it 6% germanium dioxide, these coefficients change slightly. Okay? So for example, now A1 becomes okay, so you can see the change here, right? It's not much, but it is significant when we look at the dispersion. Okay, so remember the dispersion is the double derivative of this curve, right? Similarly, B okay. So again, B's have changed slightly, you can see. So now, so that means this curve would have changed very, very slightly, right? But if you plot, for example, these two curves on this n versus lambda, you might not even see the change on this scale with naked eye, right? But when you take the double derivative, the change shows up. So, for example, if I plot now the material dispersion here, so remember that was minus lambda over c, and then second derivative of n with respect to lambda. Then picosecond per nanometer per kilometer. Okay, so recall for pure silica, the curve looks something like this, right? So it crossed zero here. So this wavelength where it crosses zero is called the zero material dispersion wavelength. Okay. So that was 1.27 micron for pure silica. Now with doping, we can shift this zero dispersion wavelength slightly. Okay, so as we increase the doping with germanium, this curve shifts slightly like this. Okay, so basically you can see from here, you can shift the, so okay, this middle dotted line here, this is for 6% GO2, this one, and then this one here is for even higher 19% germanium. Okay, so you can shift the zero dispersion wavelength here almost up to 1.4 micron. Okay. So basically you can shift the zero dispersion by sort of like tens of nanometers by doping. And that will also change the dispersion. So for example, if you're working at 1.55 here, you can see that the dispersion value will change slightly with doping. Okay, and we dope anyway because, for example, we want an index difference between core and cladding, right? So we do doping anyway. Fibers. Okay. And then from the next class, we'll see that using waveguide dispersion, how we can modify this curve even more and get the dispersion sort of suitable to the application we want. So let's now discuss how basically a transform limited optical pulse broadens in a dispersive medium. Okay. So as we discussed last time, basically we said that the broadening, pulse broadening is just given by so it's a product of the length of propagation times this dispersion coefficient times the bandwidth, right? And typically for incoherent sources where the bandwidth is determined by the source, we just take the source bandwidth and use that, right? But nowadays we use basically single frequency lasers where basically the right, so we use a laser which has a fixed frequency. Okay, so the line width is practically zero. Okay, so to give you some sense of scale, so the delta nu, the frequency bandwidth is less than 1 megahertz. So if you look at it in wavelength, and that's like less than 10 femtometer at a wavelength of, let's say, 1.55 micron. Okay, and recall, so for LEDs and laser diodes, we were talking about bandwidths of nanometers. Here we are talking about femtometers, so we are down by like 6 orders of magnitude. So basically, for all practical purposes, the this is basically a single frequency, right? So basically, what I'm saying is the light coming out of this, if you look at the spectrum, it's just a delta function at, right? And then basically what is done is we use an electro-optic modulator. So we have some electrical data here, right? Let's say some bit stream. So this is electrical data, right? And then using this electro-optic modulator, you make these into optical pulses. Okay. So these are now optical pulses. Okay, so let's say they have some width again, tau naught, right? So recall, so we said that the broadening, so now we send it through some length of fiber, right? Let's say some SMF length L, and now here basically they broaden out. Okay? So okay, and this broadening we said, right, depends on this length times the dispersion coefficient times the bandwidth. Right, so now the source bandwidth is basically 0. I mean, on the scale they're looking at, right? So tau naught again typically is like picosecond scale. Okay, so so where does the broadening coming from? When the source has basically 0 bandwidth. Okay, where is the broadening coming from? So as we discussed briefly, that basically once you have pulses here, right, just from Fourier transform relations, because you have now a finite temporal duration waveform, then basically its spectrum will have a finite set of frequencies. Although you started from a laser which had a single frequency, right? So, for example, if you take the Fourier transform this guy, the pulse you will see some spectrum, right? which will have some width. And we said now the width will depend on the pulse width. Okay. So that's where the bandwidth is coming from now, just from fundamental time frequency relations, not from the source. Okay. So basically, let's look at this phenomenon in a bit more sort of mathematical detail to see how actually these pulses broaden. Okay. So again, these pulses at the input. Okay. So at z equal to 0, let's assume the pulses to have some Gaussian envelope. So, right. So this is like Gaussian function here, and the carrier frequency here is omega naught. Right. Right. So we don't have many of these phase fluctuations now that we talked about last time. Right. So for incoherent sources, we have these phase fluctuations here, which basically give you a large bandwidth, much bigger than this, right? So that basically the source determines the bandwidth. But here for a single frequency laser, we have no phase fluctuations, so that's my lifting field. Okay, so this looks like again, if you plot, so it has a Gaussian envelope. And then a carrier frequency omega naught, right? So this envelope is, and this is the carrier frequency. Okay, so if you take, so this is the electric field. If you take mod square, and that will give you the intensity, right? So the intensity will just look like the envelope. So I of t will just be some a naught square into minus 2t square. Okay, so it will just be a Gaussian function. Okay, so now, so this kind of pulse will have some spectrum, right? So you can find out the spectrum at the input by taking the Fourier transform. Okay, so we just find the Fourier transform. Okay, so now we have some Gaussian type of integral here. Okay, so there is a e to the minus t square term, and there is also some e to the some constant times t term. Okay, so this integral looks something like so it's of this form. Right? So a here is 1 over tau naught square, and b is I times omega minus omega naught. Okay, so this is a standard integral which has an analytical form like this. Okay, and this works for even if a and b are complex numbers. Okay, so this formula works even if a and b. So here b is a complex number actually, right? I times omega minus omega naught. So if you use that formula, you get the input spectrum. Right, so we have e to the b square by 4a. So b is again I omega minus omega naught. So b square is minus omega minus omega naught square. And then a is 1 over tau naught square. So we get 4 by tau naught. Okay. So again, if you write this as some Gaussian function, right? So this is a Gaussian function centered at omega naught, and the width, right? So this is delta omega. If I write it as then delta omega square, then you can see that the width in the spectral domain is 2 over tau naught. Right. So what we are saying is so. Right, so the width here was tau naught. The width here is delta omega, which is equal to 2 over tau naught. Okay, so it's proportional, inversely proportional to tau naught, as we argued. Right? But here we can see what the exact relationship is. It's 2 over tau naught. Okay, so let's look at some practical numbers. Right, so typically, let's say, so tau naught is usually tens of picoseconds. So let's say tau naught is 20 picosecond. Okay, at a wavelength of 1.5 micron. Okay, so 20 picosecond means like the bit rate. Usually, the bit rate one can have is like let's say roughly 1 by 4 times the pulse width, right? Because basically we want the bit duration to extend a bit longer than the pulse duration, so that it goes to sort of 0 before the next bit starts. Okay, so this you can see comes out to be about 12.5 Gbps for this. So which is a typical sort of data rate. Okay, so for this wavelength omega naught is about 10 to the 15 radians per second. Okay, so in this telecom wavelength range or near infrared wavelength range, typically, so the omega naught will be in 10 to the 15. And so now delta omega is 2 over tau naught, right? So you see you get 2 over 20 into minus 12, right? So that's 10 to the 11. Okay, so delta omega is 10 to the 11, omega naught is 10 to the 15. Okay, so basically what we are saying is that the fractional bandwidth, which is the actual bandwidth divided by the center frequency, so you can see here it's about 10 to the minus 4. Okay, so this is much less than 1 for most kind of practical applications that we use optical pulses for. Okay. Only in certain extreme conditions does the bandwidth sort of extend much wider so that it becomes comparable to omega naught, right? So for that, either you have to go to very like single cycle kind of pulses, right? One or two cycles just in the pulse, or you have to broaden the spectrum using some other techniques, like some nonlinear optical techniques. Okay, apart from those special cases, especially for optical communications, this is the regime we are working. Okay, so as long as you have picosecond pulses at near infrared wavelengths, basically you have this condition that the fractional bandwidth is very, very small. Okay, so on the absolute scale, right, if I plot, so let's say this is 0 and we are plotting the spectrum, right, so it looks very sharp, right, on the absolute scale. Okay, so it's very small, but it's not 0, right? That's sort of the argument, because if it was 0, then there would be no broadening. But because it's small, we can make certain approximations while calculating how the pulse propagates. All right, so yeah. So now, let's say after a propagation length z in the fiber, right, if you want to calculate the electric field at distance z as a function of time, right? So basically, again, what we can do is, we know the input spectrum, right? So we know basically sort of the amplitude at each frequency, okay? And we know basically how monochromatic waves propagate through the fiber, right? It's just like the mode propagating, right? For a single frequency, we have some particular propagation constant beta, and it just acquires a phase e to the minus I beta z, right? So what we can do is easily find the spectrum at z, and then take again the inverse Fourier transform. Okay, so the spectrum at z is just the input spectrum multiplied by the phase factor e to the minus I beta. Okay, so for each different omega, this beta will be different. Okay, and e to the I omega t phase is already taken here, so okay, so that's why we only take the beta. Okay, so now we use this condition to basically approximate a function for beta of omega. Okay, so we do a Taylor expansion. Okay, so basically the values, although this integral runs from minus infinity to infinity, basically the only values contributing are these very sharp, just like from sort of omega naught minus delta omega to omega naught plus delta omega. Right, very small range of frequencies is actually contributing to this integral. Okay, so in that very small range, we can do a Taylor expansion of this function beta of omega. Okay, so we can do a Taylor expansion about the center frequency omega naught. Okay, so the first term will be the first derivative of beta times omega minus omega naught. Then the second term will be the second derivative omega minus omega naught square, and you could take higher order terms also as many as you want. But again, we'll make the argument that since this bandwidth is very, very small, up to second order is sufficient. Okay, taking higher order terms doesn't increase the accuracy too much. But again, in case in the future or somewhere you encounter a case where this fractional bandwidth is not small, then you'll have to take into account higher order terms. Okay, so this is just the propagation constant at the center frequency, the carrier frequency. So let's call that beta naught. So this is 1 over the group velocity, right? Derivative of this is 1 over group velocity, right? Evaluated at the center frequency. So that's the group velocity of the pulse. And now here we have the second derivative, right? So this is beta 2. Okay, so this is beta 2, the GVD constant, again evaluated at the center frequency. Okay, so basically we plug this approximation Taylor expansion for beta omega into here. Okay, so you can see that, so I get a, so I have terms like omega minus omega naught. So basically I can write this omega as omega minus omega naught plus omega naught. And then I'll have a beta naught here. So that gives me I beta naught z. So basically I can take this term e to the I omega naught t minus beta naught z, which is the phase acquired by the carrier frequency, right? So if you just had the carrier frequency traveling, that will acquire this phase, omega naught t minus beta naught z. And then we have some other part remaining in the integral, which we call, because so this is a pure phase, right? This is what we call the envelope of the pulse. Right, so this is the pulse envelope at z. So Az of t, you can see once we plug this in here. Okay. Right, so we took e to the I omega naught t outside, so inside we are left with e to the I omega minus omega naught t. That's this first term. Then from this term we have a omega minus omega naught by Vg times z. That's the second term. Right, and this term will give me this term. Okay, and so now you can see this is some phase here, right, which depends on frequency, right? So this is some e to the I frequency dependent phase, right, that we discussed last time. Basically gives you chirping and broadening, right? So you can see that there is a frequency dependent phase which depends on the propagation distance there. Okay, so let's do this change of variables here to again get it into a form that can be evaluated. So here if we put capital omega as omega minus omega naught, so this omega is known as detuning, right? Is the shift from the center frequency. And so write the integral in omega minus omega naught form. And also, so remember we had expression for E of, since the input spectrum we had an expression for that already, right? This was right. So yeah, we plug this expression for this also, and then do this change variable. So the integral becomes, so square root of pi. Okay. So yeah, everywhere and anywhere you had omega minus omega naught, we now have capital omega. And so terms proportional to omega square came from here, right? Tau naught square over 4, and then from this GVD term here, beta 2z, and then the term proportional to omega comes from here, with t minus z over bg. Okay. Expression, which expression is not visible? Is this expression not visible? Okay, let me write that. Yeah. Okay. So again, you can see that this integral is of the same form that we used in the beginning to calculate the spectrum, right? This integral runs over capital omega, and there's just e to the omega square term and an omega term, right? So this is again of the same form. Right, this form. So basically, you use the same formula. Okay. So basically, we get the pulse envelope at a distance z. Okay, so immediately some things to note here. is that the envelope still looks like a Gaussian, right? Except that now it's centered at z over Vg. This is like e to the t minus t naught whole square divided by some constant. So this is also still a Gaussian function, except now it's centered at z over Vg because of course the pulse has moved, right? Pulse is moving with the group velocity. So now it's not centered at z equal to 0, but it's centered at z equal to Vgt, right? So that's the first thing. Second thing is the amplitude has gone down, right? So we started with a naught. Now it's a naught divided by something which is bigger than 1. So the peak amplitude has gone down. And also here, instead of tau naught square, we have tau naught square plus something, which means that the width has gone up, which means it has broadened. Right? So it's easier to see if we, for example, so since these are complex numbers both here and here, what we do is write this as sort of a real number magnitude times a phase. Now the phase will also be time dependent. Okay, so yeah, if you just take the magnitude and phase or angle of that complex number, right? So you can write okay, so this will be the mod of AZ part, right? So again, so now you can clearly see this looks like a Gaussian function. Okay, we'll define what tau z is, and then this e to the I phi t part. So this is multiplied by okay, so this phi of t here is this. Okay, so this first term is coming from like this, taking the imaginary part of that, right? And then the second, this term is coming from taking the imaginary part of this. Okay, so what are tau z is basically the pulse width at z, right? So you can compare this to that expression and see tau z is okay. So it's something bigger than tau naught, which we started with, right? So that means pulse is broken. Can you please summarize why we are taking Fourier transform of incoming beam? I mean, our task is to, okay, so you're given some input pulse, right? So this is some A, right? So this is at z equal to 0. Then after just at some z, it goes up to L, right? So this is some a at z equal to 0 of t, right? So that's the pulse we are given starting with. We want to see what the pulse looks like after it propagates through the fiber, right? So a at L comma t. That's what we want to do, right? So how do we do that, right? What we know already from modes in the fiber is that so for any particular frequency from the solutions to the modes in the fiber that we've looked at, right? Given the particular mode, so any given frequency we have a particular propagation constant, right? So for example, single mode fiber, only the LP01 mode will be there. So for that, for example, we have a BV curve, right? So given a particular frequency or a V number, we know what the propagation constant would be, right? So that means if I start with a monochromatic wave at frequency omega, we know that basically the only thing that happens to it is basically it acquires a phase e to the I omega t minus beta, right? Because that's what a mode is, right? It just propagates and acquires a phase, right? So we know how a single frequency propagates through the fiber, that we know, right? So basically we want to use this fact to calculate how the pulse propagates, right? So how do we do that? So first we take a Fourier transform, right? And then find out what the spectrum is, right? So now you know what is the amplitude at each given frequency at the input, right? So a temporal pulse basically is just a collection of different frequencies with different weights, right? So you calculate what those weights are by taking a Fourier transform. So you calculate what those weights are at the input, right? And now we know each frequency just travels through the fiber like a phase. So basically for each frequency component we multiply by this phase, right? And then we get easily what we get is the spectrum here at the output, right? And then what we need to do to get the time domain is just take another inverse Fourier. Okay, so that's what we do. That's why we're taking Fourier transforms, because we know in the spectral domain what happens. We can mathematically do very easily because it's just a phase, right? So that's why you first go to the spectral domain, calculate the propagation, and go back to time. Can you read out the second term? This term? Yeah, this is kappa. Okay, so we have to define this. This is not K. Yeah, anyway, so hope this is clear why we are taking Fourier transforms. Yeah, so this is kappa times t minus z over g square. So this kappa depends on, again from here you can see it will depend on the beta 2. Okay, and this kappa is basically known as the chirp factor. So recall our discussion from last time that basically what why the pulse is broadening is that the different frequencies are traveling at different group velocities due to this beta 2, right? Group velocity dispersion, and that leads to chirp. Different frequencies now being delayed with each other, right, within the pulse. For a mode, normalized frequency parameter and omega. No, normalized frequency is V, right? Normalized frequency is the V number. here omega is the absolute, the angular frequency. So omega is 2 pi c by lambda. And normalized frequency V is that k naught a square root n1 square minus n2 square. Right, so why is this called the chirp factor? So you can see here, so now the phase, right? So we have some phase here, right? Which, so you can see, so it looks like e to the I kappa t square. Right, so now whenever you have a phase like this, right? So comparing this to e to the I omega t, we can define an instantaneous frequency okay, which is basically the derivative of the phase. Okay, so now if you take the derivative of the phase, you can see here basically this is kappa times t, right? Because the phase is kappa times t square. The instantaneous frequency is kappa times t, which means the frequency is now time dependent, right? Which is what is a chirp, right? And now you can see that the sign, so kappa is basically beta 2, which means, so if beta 2 is positive, which is normal dispersion, this slope is positive, right? Which we also discussed last time. So omega t is 60, so this will be positive if beta 2 is greater than 0 or d is less than 0, and it will be the opposite for the opposite case, right? So now you can sort of rigorously we've derived how the pulse chirps, and so the chirping also leads to broadening. And along with the broadening, the peak amplitude goes down, right? That is to conserve the pulse energy, right? Because we are not losing any, we haven't taken any loss or anything. So the total pulse energy remains the same. So as it broadens, the peak amplitude goes down so that the integral in the pulse remains the same. Okay? So for example, so now if you want to find the intensity or the power in the pulse, right, we need to take the mod square of this, because this was, remember, the electric field amplitude. Right, so the intensity or power will be proportional to mod square of this. Right, so that you can see will look something like, so I of z comma t will look like I naught times okay. So now you can check for yourself that, so the pulse energy right will be the integral of the intensity over time, right? Area under the curve. Okay, so you can check that this will be a constant that is independent of z. Okay, so which means basically, so this is your pulse intensity. So as it propagates, so I start out with some width tau naught. As it propagates, it broadens, right? And the peak amplitude also decreases, right? So this is at z equal to 0, this is at some distance z, let's say this is at the output L, right? So this is now tau of z, this is I naught, this will be I of z. Right, so basically the area under this curve is the total energy in the pulse. That would be the same for all, for any position. So the pulse energy has to be conserved because we haven't taken any loss. Right? So that's how the intensity of the power in the pulse looks like. If you want to check the electric field, right? So again, we start with the pulse, which is transform limited, right? So this was a0 of t. So this was Gaussian envelope times, right? And so now, after propagation, what happens is this broadens, right? And also now there's a chirp. Right, so this is the time axis. This is z equal to 0. Let's say this one z equal to L. Right, so this case would correspond to lower times. So the lower frequencies are arriving first, and then the higher frequencies are arriving later. So omega t versus t is positive, right? So this means beta 2 is positive. So this would be the beta 2 positive case. Okay. I just erased the broadening, but the broadening. So this tau of z was proportional to beta square. It just depended on the square of beta 2. Okay, so basically positive or negative doesn't matter for the broadening, right? Where the sign of beta 2 shows up is in the chirp. Okay, and so yeah, if this is the time axis, basically now this pulse is now centered at t equal to L over bg, right? So the wave packet is moving at Vg, but it's also broadening and chirp because of beta 2. Okay, now if we calculate explicitly the broadening, so we have an expression for the pulse width at distance z. Okay. So if we just calculate, so what is the broadening after a length L? Okay, you can calculate like this. So this is also known as the root mean square broadening. Okay. So yeah, if you just plug in the expressions here, you can see you will get L times beta 2 times 2 over tau naught. Okay, so basically if we define this 2 over tau naught as the bandwidth, which we already saw in the beginning, right, from the Fourier transform, then basically this is just L times beta 2 times delta omega, which is basically what we initially had expected, right, from just the definition of the broadening. So yeah, it's consistent with that if we take the bandwidth to be the Fourier transform bandwidth of the path.